The spanning tree gives us a loop-free route from one city to every other city. But the spanning tree algorithm did not consider the edge weights, so the calculated routes may not be the shortest. Let's now see how we can utilize the edge weights to find the shortest or minimum distance route between two nodes. We will still utilize breadth-first traversal or BFT, but we're also going to record the total distance from the origin to all the nodes. If one route to a particular node is shorter than another route, we will replace the longer route with a shorter route. Let's begin with a small example. Suppose we have this following network. And here are the edges in this graph. Suppose that our origin city is A, and we want to find the shortest path to city C. As with the spanning tree algorithm, we're going to construct a new tree with the shortest paths to the nodes. The node format is node value distance parent. The value is the node value. The distance is the sum of the edge weights in the path from the origin to the node. Parent is the parent node value. Initially, the shortest path tree just has city A. The distance from node A to itself is 0. Node A is the root, so it does not have a parent. And here is the same tree as a table. As with BFT, we first consider the neighbors of node A, which are B and D. Since B and D are both directly connected to A, the total distance from A is simply the edge weight. The edge AB has weight 4, so the distance from A to B is 4. And the edge AD has weight 7, so the distance from A to D is 7. Let's now add B and D to the tree. The tree is a stack, so we push to the top. Next, let's take a look at node B. Node B's neighbors are C and A. First, we calculate the total distance from A. The distance to C is the distance from A to B plus weight of edge BC, which is 4 plus 6. Distance from A to B was 4, and the distance from B to C is 6, so the distance from A to C is 10. Let's add C to the tree. The distance to A is distance from A to B plus the weight of edge BA, which is 4 plus 4. If we traveled from A to B and then back to A, the total distance is 4 plus 4 or 8. Node A already exists in the tree. If a node already exists, we compare the calculated distance, which is 8, against the existing node distance. If the calculated distance is shorter than the existing node distance, then the node's distance and parent will be updated. In this case, A's existing distance is 0. The new distance is greater than the existing distance, so A remains unchanged. This makes sense, since the distance to travel from A to B and then right back to A is always larger than just staying put at node A. Thus, the table remains unchanged. Next, let's take a look at node D. These neighbors are A and C. The distance to A is the distance from A to D plus the weight of edge DA, which is 7 plus 7 or 14. 14 is greater than the distance value of A, which is 0, so node A remains unchanged. The distance to C is the distance from A to D plus the weight of edge DC, which is 7 plus 1 or 8. 8 is less than the current distance to C, which is 0. we have found a new shorter path to C, so we update node C's distance to 8 and the parent to D. As we can see from the graph, the original path from A to C was through B, and A to B is 4 and B to C is 6, so the total distance is 10. But when we go through D, A through D is 7 and D to C is 1, and 7 plus 1 is 8. So going through D is actually shorter than going through B. Finally, let's consider node C. C's neighbors are B and D. The distance to B is the distance from A to C plus the weight of edge BC, which is 8 plus 6, or 14. 14 is greater than the distance value of B, which is 4, so node B remains unchanged. The distance to D is the distance from A to C plus the weight of edge DC, which is 8 plus 1, or 9. 9 is greater than the distance value of D, which is 7, so node D also remains unchanged. Thus, the table remains unchanged, and the shortest distance from A to C is 8 via D. Here's a video demonstration.